Welcome to Networks Professionals.
Welcome to this explainer. It's so easy to just marvel at modern AI from the outside, but today we're popping the hood. We are going to look at the hidden mathematical engines that actually give neural networks their ability to learn. It's the secret sauce of AI, activation functions. To really grasp why these matter, we kind of have to start with this massive, frankly fascinating, vulnerability. We constantly hear about deep neural networks, right? These massive models with dozens or hundreds of layers processing mountains of data. But here is the wild secret. Without one very specific mathematical spark, the deepest, most complex AI networks out there, they fail completely. They become functionally useless. So the big question we have to ask ourselves right out of the gate is, what actually stops a deep neural network from just collapsing into basic math? What keeps it from flattening out into nothing more than a highly inefficient calculator? Well, that brings us right to section 1, the linear regression trap. Here is the fatal flaw. Without activation functions, your fancy multi-layer network literally collapses into a simple linear regression model. I mean, literally. The deepest 1,000-layer network just flattens into a straight line. But the moment you introduce these functions, everything changes. The models suddenly unlock the ability to learn complex, non-linear patterns. They are the absolute critical difference between a network that can only draw a straight line and a network that can actually wrap its head around the true complexities of the real world. So, how do we actually fix this fatal flaw? Let's move to section 2. Enter the gatekeepers. In a practical sense, activation functions act a whole lot like the biological neurons inside our own brains. For every single node in the network, they make the ultimate decision to either activate, meaning, fire its signal forward, or to just stay completely silent. They sit right at the end of a neuron, they look at all the data rushing in, and they make a choice. And that introduces the formal concept of thresholding. I want you to think of these functions as literal gatekeepers standing guard. Their entire job is to decide if a neuron's weighted sum of inputs is actually significant enough to pass on to the next layer. They calculate all the data hitting that specific point, weigh it out, and apply a strict threshold. If the incoming mathematical signal doesn't have the right weight, the gate stays closed. The signal dies right there. But if the weight of those inputs is significant enough, the gatekeeper swings the door open and passes that signal deeper into the network. And the crazy part is, this thresholding process is happening millions of times a second across the entire network. Okay, let's jump into section 3, the power of nonlinearity. The actual superpower of a neural network comes from injecting this nonlinearity. That is what allows them to learn complex mappings of real-world patterns. Because let's think about the real world for a second. Human speech, it's not a straight line. The pixels making up a photo of your dog, definitely not simple linear math. Real-world patterns are incredibly complex, messy, and tangled. By injecting nonlinearity into the system, the network completely breaks free from that linear regression trap we just talked about. It suddenly gives the AI the power to bend, curve, and actually map itself to the chaotic reality we're asking it to understand. Which leads us perfectly into section 4, 3 essential activation functions. Today's most sophisticated models basically rely on a primary arsenal of these gatekeepers. First up, we have ReLU, that's the rectified linear unit, which is famous for its sheer computational efficiency. Then we have Sigmoid, which maps inputs to a very specific range between 0 and 1, making it heavily relied upon for binary classification. And finally, Tanh, which is pretty similar to Sigmoid but maps its outputs between -1 and +1. Each of these mathematical formulas has a highly specific job and a totally unique way of applying that thresholding logic. Take ReLU, for example. It passes positive inputs through directly, but, and here is the trick, it snaps any negative input exactly to 0. That's it. Got a negative number? Boom, it's a 0 now. This surprisingly elegant little trick dramatically boosts computational efficiency. Plus, it helps fix what's known as the vanishing gradient problem. That's this major issue where signals essentially just fade out and die as they travel through really, really deep layers of a network. By snapping those negative values to an absolute 0, ReLU keeps the math from fizzling out, which allows data to flow cleanly through massive models. Then we have Sigmoid and Tanh. So Sigmoid maps inputs strictly into a range between 0 and 1. Because of that hard boundary, it forces the math into a framework that gives us a clear probability. That makes it your absolute go-to for binary classification. When a neural network needs to make a firm yes or no decision, Sigmoid is the one handling the math. Now, Tanh uses a very similar smooth, nonlinear curve, but it stretches it across a broader scale, specifically between -1 and +1. This is absolutely perfect when the network needs to balance out data that has both strong negative and positive mathematical weights. All right, let's wrap this up with Section 5, Powering Modern AI. Here is the reality. Without these exact functions, without ReLU, Sigmoid, and Tanh, the modern tech that you and I use every single day simply would not exist. Think about image recognition. When your phone unlocks just by looking at your face, that is a neural network mapping complex nonlinear patterns. Speech to text. When you dictate a message to your phone, it absolutely requires nonlinear thresholding to decipher the totally chaotic audio waves of a human voice. Even recommendation systems. The algorithms perfectly curating the videos you watch or the products you buy, they rely entirely on those tiny mathematical gatekeepers deciding when a neuron should fire and when it should stay silent.
So we've seen just how crucial these activation functions are for saving our models from that linear regression trap, and how they provide the flexibility needed to understand our very messy world. But as artificial intelligence continues to map even more complex realities, and as these networks grow deeper and way more sophisticated, what new mathematical gatekeepers are we going to need to invent? How are these functions going to evolve to unlock the very next level of machine learning? It's a wildly thrilling question, and honestly, one I hope leaves you wanting to dig in and explore it even more. Thanks so much for joining me on this explainer.
Thanks for watching.